In this tutorial, we're going to take a look at the inverse of a quadratic function, and we're going to start with this example, the equation that relates distance, and d is in meters is the distance, falling for a skydiver after t seconds is d equals 4.9 times the time squared. And so we're asked here, how far would the skydiver fall in 10 seconds? So that's not an inverse question at all, but that's where we're going to start. So we would just substitute the 10 in place of the time. And so we'd evaluate it like this. We would go 4.9 times 10 squared. And that's 100 times 4.9 is 490. So that's why we'll get 490 meters. So that's how far the skydiver will fall in 10 seconds, about almost half a kilometer, 490 meters. And we're not worried about air resistance. This isn't a physics problem at all, so we won't worry about any of that at all. We're just talking about quadratic functions, and we'll get into their inverses very shortly. Now, this question, this formula right here, is solved for d. So initially, it's written so you can find a distance if you know a time, like we did here. In this example, we're asked, okay, so we have this formula again, how long would it take the skydiver to fall 1,200 meters? So in this case, the 1,200 is the d, and we're trying to solve for time. How long? We're trying to find a time. So we need to isolate for t here. So the first thing I would do is divide out the 4.9, and these are going to divide out. We're just left with the t squared on the right side. So we're dividing 1,200 by 4.9, and let's bring the calculator back. So that 1,200 divide 4.9 gives us, so that's where the 244.9, I rounded to one decimal place. And then to solve for time, we would take the square root of that. So the square root of 244.9 is going to be about 15.6 seconds. So that's how long it takes the skydiver to fall 1,200 meters. Now, if we were trying to find a whole bunch of different times, if we always knew the distance, then we'd have to do this solving for t every single time. So if we had that scenario where we wanted to find times knowing the distance, it would make sense to rearrange this and solve for t. And that's actually the inverse, because you see, this formula here takes a time and finds a distance. The inverse would take a distance and give you back the time. And so that's what we want to do here. So you see, for example, if I put the 15.6 in here, it should take me back to the 1,200. And in fact, I'm not going to use 15.6. I'm going to use the entire decimal. So you see a little ANS here, that's the last answer. So if I were to put that value in place of time as squared and then multiply by 4.9, so I could go 4.9 times that last answer squared, so that should return me right back to the 1,200. A little bit of rounding difference, that's the only reason you have this 0.01, but essentially that's what that's doing. So the inverse function takes you back to the original distance value. So that's what we're going to do in the next page here. So here's this distance curve, and I've graphed it here. That's the red one. That's the parabola d equals 4.9 t squared, and I didn't, this is actually just using Desmos online here. So this would actually be distance here and time over on this axis. And so I want to find the inverse function. And so now I'm going to solve for t. In inverses, we often switch the x and y variables, but I'm going to leave d as d and t is t, because d does represent distance and t represents time, so I'm not switching the variables here. I'm just going to solve for this variable over here as opposed to the d. So that's why I'm not switching them, because t means time here. I can't switch it with d because t means time, d means distance. So I want to solve for t here. So the first thing we would do, like when we had the 1,200 here, is divide out the 4.9. So those will divide out, and we will get time squared equals the distance over 4.9. And then to solve for time, we would take the square root of both sides. So the time will be the root of this d over 4.9. So that is the inverse. I didn't do that in my presentation. Maybe I'll just write it here. So this is the inverse. There we go. Now, so like I did in the previous page, if I wanted to find the time now, knowing the distance is 1200, then we would just plug 1200 in place of d. We would take our handy dandy calculator and go the root of 1200 divided by 4.9, close the bracket. Oh, I get 49 there. Forgot my decimal. There we go. So that should give us the 15.6 seconds again, which is exactly the calculation here. Now, a couple of things I want to show over here, and actually the red function, the original function, it is a function. I should have called it relation first. It is a function because it passes the vertical line test. When I solve for t here to get the inverse, notice I didn't put a plus or minus. If you're familiar with the quadratic formula, in front of the root sign there's a plus or minus. So because it's only the positive root, then this is the inverse here. It's only the positive half of that parabola reflected in the y equals x line. If I were to graph the negative root, that's what this is going to be here. You'll see it come up now. See, this green one is the positive root of, and I can't use t here, it has to be x over 4.9. The negative root would be the one down here. If you plot both of those together, it's not the inverse is not a function. Only if you do just the one, like that, then it's a function. So vertical line test only cut through one place. So we do something called restricting the domain of the original function, so this inverse is still a function for a quadratic. And you see, if we were to only graph this part right here, then if you reflect that in the y equals x line, you get this part right here. So we restricted the domain of this to be just x is greater than or equal to 0, which is the right half of the parabola basically, then the inverse is a function. If you do the whole thing again, it's not. So we're going to do that in the examples on the next page. We're going to find some inverses. And so starting on this page, and there's two examples here altogether, one on this page, one on the next. So it says find the inverse of the following functions, this one here, and there'll be one in the following page. Restrict the domain of the original function, so its inverse is also a function. So we're only going to restrict it to half the parabola. So when we flip it in the y equals x line, we get an inverse whose function is whose inverse is a function. So we're going to state the domain and range of both the original and the inverse. And so for the inverse here, now I'm switching x and y here because x and y don't have a particular meaning like distance and time. And the reason I'm doing that is so when we graph it, I've solved in terms of the dependent variable. Remember, this is dependent variable, this is independent variable. So I'm switching x and y, and I'm going to solve for y. So if we do that, this is what the inverse looks like. Now, it's not solved for y yet. So if one of my students were doing a test and all they did was this, I would give them a little bit of marks, but to get the full marks, you need to solve for, actually rearrange for y. Probably give you less than half. Maybe it was out of 3 marks, I might give 1 for this part here. So I want to rearrange and solve for y here. So the first thing I would do is get this expression with y alone. So I want to get rid of that plus 1. So we could subtract 1 from both sides, or some people may say move the 1 over. It'll be a minus 1 on the left. And so I left a little bit of room here because the next thing we're doing to get rid of the square, to get the y minus 3 alone, is to take the root of both sides. So I'm going to take the square root of both sides, the square root of a square. They're opposite operations, so that square root gets rid of the square here. And then I'm just left with y minus 3 on the right side. And the next thing I want to do is now I isolated for y minus 3. Now I want to isolate for y. So I want to get rid of this negative 3. So I'll bring this over here, and of course it'll be a positive 3 on the left side. So the x minus 1 plus 3 is equal to y. Now, we don't normally, because y is a dependent variable, we normally write the y on the left. So I'm just going to rewrite this with the y on the left and the root of x minus 1 and then plus 3 on the right. Be careful when you write this. The plus 3 is outside of the root, so you do not want to make it look like this. Okay, you do not want that to be there. That is not correct. Let's get rid of that. So that is that's the inverse function. So let's graph these now. So first of all, this is a parabola with a vertex. This is in vertex form. The vertex is at 3, 1. So 3 comma 1 would be right over here. And see, the a value is 1 here. So remember the step pattern, 1 comma 3 comma 5. So if we start there and go 1 to the right, you go up 1, 1 to the left, up 1. And then from each of those over 1, 1, 2, 3. And same on this side. And I'm not going to bother to do the 5, but that's enough. So that's what my parabola looks like. And of course it does keep on going. So I'm going to restrict the domain so that the inverse is going to be a function. So that's my parabola. So I'm going to restrict the domain to just this. And we'll get into that down here in just a moment. Now the inverse, this here, it would start at 1 comma 3. It's really kind of like the vertex. If we were to graph the entire parabola, that would be the whole vertex. So that's why it's at 1, 3, because this is basically the root function translated to the right 1 and up 3. So right 1, up 3. And remember, it has the same step pattern, but it goes the other way. Remember, it goes horizontal. So if I go up 1, I go over 3. Sorry, up 1 over 1, and then up 1 over 3, for example. And I could do 5 as well if I wanted. So that's my inverse function. Remember, you're only graphing half the parabola. You do not graph this bottom here, and then it wouldn't, because it would not be a function then. So that's my root x minus 1 plus 3. If you're graphing the bottom part, then you have a negative here. So the domain of the parabola is normally all real numbers, but we're going to restrict it to just the right half of the parabola. So since x is 3 there, we're talking about just where x is greater than or equal to 3. And the the range of that would be the lowest y value is 1 here, and the y values are higher than 1 everywhere else. So y be greater than or equal to 1. Now for the inverse, see the inverse, the lowest x value is 1 here, and then it increases without bound towards the right. So the domain is all real numbers greater than or equal to 1, and the range, the lowest y value here is 3, and of course the y values increase without bound as you go along here, and you get bigger and bigger and bigger. Remember, there's something special between the inverse and its original function. The domain and range just switch because remember we switched x and y. So this is the domain of the original function, same set of numbers here, of course y instead of x. In the inverse, the range of the original function, that set of numbers is the same as the domain of the inverse. And that's always the case in any original and inverse functions. Parabolas are not. One more example in B here. We're going to do the same thing as in the previous page, and we're going to graph this first. So the vertex would be at -5, -1, which is that point right there. And so the step pattern's been altered a bit here. So we're multiplying it by -1/4. So then this would be -1/4 or -0.25. Multiply 3 by -1/4, it's -3/4 or -0.75. And then the 5 would be -5/4. So if we started our vertex here and see go right, you're only going down 1/4. That's why, see, there's the first one right there. So that would give me that point about right there, that point about right there. And then down -3/4. So from here, you know, it's going down a little bit more. I guess it actually should be here. I guess I'm off just a little bit in my graph. Let's fix that. There, that's a little bit better. It's not perfect, but that's the limitations of drawing in PowerPoint here. So I went down 1/4, and then see if I went down another 3/4, it should be around 1 down. And then we would go over 1 and down, well, about 1 1/4. I'm maybe off slightly a bit, so just below this a little bit here, but that's the idea. That's pretty close to what the parabola should look like. So that's the original. So let's find the inverse now. That's my original function. So the inverse says we switch x and y. We want to solve for y, same as the one on the previous page. So there's my switching of x and y. And to isolate for y, I would isolate for this expression first. So I want to get rid of that -1. So we'll bring the -1 over to the left, be x plus 1 equals this. And I'm leaving some room here because I want to isolate the y plus 5 squared term. So I need to get rid of this -1/4. Now I could divide both sides by negative a quarter, that works, or because it's a fraction, dividing by negative a quarter is the same as multiplying by negative 4, multiplying by the reciprocal of negative a quarter. And you see that isolates for y because this 4 will divide with this 4, and then negative, well, there's negative 1 there now, basically, times negative 1 is positive 1. So this whole thing here will end up just being a 1. So let's get rid of the writing. And so we have just y plus 5 squared on the right now, and of course, don't forget the x plus 1 does get multiplied by this negative 4. I'm not going to bother actually multiply the 4 in, because it's really going to be in a more factored form, a transformational form, so that's why I'm leaving it like that. Now I want to solve for y plus 5 now, so I need to get rid of the square. So then I'm going to take the square root of both sides, and now the square root of 4 is 2. You could leave the 4 in here and think of it as horizontal, it would be compression, or you could bring the 2 outside and have it as a horizontal, vertical stretch, sorry. So whichever way you want to do it, it really doesn't matter. So that's what it looks like now. To isolate for y, finally, I'll bring the 5 over here. So it'll be that root minus 5 equals y. Now remember, the negative in here just means a reflection. This is definable as long as this is going to work out to a negative times that negative 1, then we're taking the root of a positive. So it's not like this is undefined because of the negative there. And of course, we want to normally write the y on the left. So that's my inverse function. So this is our parabola. So if I restrict the domain to this right side, that's the positive side of the parabola. So that's why I'm doing that there. Then the inverse of that is going to be a function. So the inverse would look something like this. See, it's a root function that's been translated 1 to the left and 5 down. So 1 to the left and 5 down. That's why it starts right here. That negative means that instead of opening this way, it opens this way. And so that's how we know to graph it like that. So that's my inverse function. The domain of the original function, I'm restricting it to x values greater than or equal to negative 5. And the range, highest y value there, because the vertex, remember, was at negative 5, negative 1, y is less than or equal to negative 1 there. And so for the inverse, the domain is x is less than or equal to negative 1. Remember, just the same set of numbers here, but x for domain instead of y. And the range would be y is greater than or equal to negative 5, because that's the lowest y value. As you go up on the graph here, y becomes larger and larger, even positive up here. So that's the range of my, my inverse. And again, remember, those sets of numbers are the same. These sets of numbers are the same because it's an inverse. And that's the end of the tutorial.